Yeah, so are you able to see my screen?
Yes.
Yes, ma'am.
Yes, ma'am.
Yes. Okay. So so the second lab assignment is out. It's on this multi-agent search. Okay, so it's basically whatever we've seen on min-max, expected max, and this notion of pruning. Okay, and also you will design your own evaluation functions to help in the pruning process. Also, you will use your evaluation functions. So yeah, so I think it's now you're all familiar with this framework. So just follow the same procedure that you did, like going through the instructions, trying to replicate some results and all that. Okay. So for this, the deadline is October 6th, I guess that's what I said. So it's a little bit before your midterm. I think it's the same week, but a few days before your midterm starts, maybe 2 days before the midterm. So I would encourage you all to start working on it early, okay, so that you don't get stressed out. Okay. So yeah, fine. So any questions so far? Any concerns? Anything about the course that you know that concerns you, or is there anything you want to talk about? All of you are fine with the course and the assignment and the pace and everything? Okay, I need somebody to speak.
Yes, ma'am.
Yes, ma'am.
Yes? Okay.
Yes, ma'am.
Okay. Fine. Great. Okay, so let us get back to what we were looking at. So we started the topic of MDPs last time. So this was Markov decision processes, and so I felt that I kind of rushed a bit in the last time. So I just wanted to specifically mention a few points which I missed. So let me just go through a summary of this. So in search problems that we saw, like we had these actions which take you from one state to another, and you always knew that if you take one action you're going to land up in this state. Okay. But now we are adding one more sophistication where if you take an action, it's not guaranteed what the next state would be. Okay, so there's a probability, there's some randomness in the system, due to which you might end up taking some other. You might, if you take an action, but you might end up visiting any of these states. So there's a probability of visiting any of these states. If you are in state S and take an action, any of these states S dash can be visited. Okay, so that there's a probability of that, and this is a conditional probability. And we saw, we just analyzed it a bit further. So what is the distribution over, what is the random variable, all these things we saw. So here the random variable was this S dash, that was the random variable. It's random over the states, over the destination states. Okay? These quantities are given. So there are two states here, state where you start and you take an action, and where do you reach. So the destination is what is random. And here additionally there was a component called a reward. Okay, so for each transition there was also a reward. So if you took an action S, if you were in a state S, took an action A, and suppose you finally landed up in S dash, then R S A S dash, that was the reward. Okay? So each transition carries a reward. So this was something which was not there in the case of regular search problems. Okay? And even the multi-agent search, you didn't see this notion of rewards. You only had a terminal state and some terminal rewards. But here there is a reward associated with each action. And again, you had the start state. And this terminal, so it is not very meaningful in the case of MDPs, but sometimes it's just used to represent the end of the process. So after this, no more actions you take. So something like that is what the terminal represents, as opposed to what you had in the case of search problems, where the terminal was like a goal state. Or, of course, you end there, but it was more to do with also the rewards, because you had rewards only at the terminal. So then we saw this example of a robotic car, and all of you had thoughts on what the rewards should be. So you had like 3 states, like cool, warm, and overheated. The engine is in one of these 3 states, and your objective is to go to some destination, but also keep the engine in a stable state. So if it becomes overheated, then the machine gets damaged. Okay, so you don't want that. So what is the sequence of actions? So actually, all these these MDPs, what they do is help you make some decisions in a sequence. So one after the other, you have to take a decision. One after the other, you have to choose an action, and so it's a sequential decision making process that the MDP models. Okay. So this was the transition model we had, and here we also wrote the rewards. So the associated with each action there was a reward. So for instance, to go from the warm to the overheat state. So this action had a reward of -10. So it was an undesirable state, undesirable action. Okay, so like that, you constructed the transitions, and so yeah. So one thing I also wanted to mention, which I missed, is a very crucial one, is this term Markov, right, that we use in MDPs, right? So the Markov in MDPs, where does it come from, right? Any thoughts where it comes from? Have you seen something about Markov earlier in your any other courses?
Markov chain.
Markov
In
chain.
probability.
Markov chain, right? Yes, exactly. So this is exactly the same assumptions that you have in Markov chain. So so somebody typed something. Probability in statistics course. Exactly. So you would have seen Markov chains there. So it's the same. So do you remember what the Markov assumption was there in Markov chains? So let's just recall a bit of Markov chains. So you had some states, maybe something like this, and you had some transitions, right? Something like, and there was some probability of going to each of these states, right? Something of this form, and there's this process that was there. So so what was the Markov assumption? Do you guys recall that?
The next state, all the information required to get next state can be attained from the current state.
Yes, exactly, right? So so basically in Markov chains, what you had was this was also something which evolved over time. So you had at each time you had a state. So S0, S1, S2, like that it went on. So okay, yeah, so at each time you had a state, and what you had was probability that st plus 1 equal to some s, given all the history, right? St equal to, maybe let me just write it as st minus 1, like that. So what it means is st equal to something, st minus 1 equal to something. So when all this was given, what this had was, it didn't depend on anything which occurred before t. So if you knew what happened up to time t, all that you care is exactly what happens at time t, right? So this was what you had in Markov chains. So you can basically ignore all of this information from t minus 1 all the way what was there behind, and focus only on what happened in the time step just before. Okay, so it's like nobody cares about your past. Okay, so just one step before, how were you doing, and so that lets you decide where you will be in the next iteration or the next time step. Okay, so that was what you had in Markov chains. Okay, now here in Markov, in MDPs also, it's a very similar thing. So anybody wants to tell me, like, what do you see as the difference between MDPs and Markov chains? What do you notice as the difference?
There are rewards in MDPs.
Yes, so yes, that's one thing. So let's just write this: Markov chains versus MDPs, right? So one difference is MDPs, you have rewards. So rewards in MDPs. Anything else?
terminal state.
So terminal state, okay. So terminal state is not very crucial in MDPs. It's not mandatory, but let's anyway put it. Terminal state in MDPs. So not crucial. I'll just write it here so that it's clear. So it's not very crucial. Any other thing that you see?
Actions.
Actions, right? Exactly. So that's one of the main things that distinguish the two. So in a Markov chain, you just have these transitions. So maybe this has a probability 1. So the probability of going from S to A is 1. And maybe this is like a 0.75 and 0.25. So these two, whatever comes out from a state has to be 1. And here again, this would be a 1. Okay, so there is nothing like an action in a Markov chain. But whereas in an MDP, you have these actions, and for each action, there is, it's like a further division of a Markov chain. So each transition in the Markov chain, it's as if it's split into, multiple parts based on what action you take. Okay, that's one way to think of it. From cool, like you had with fast, there were two possibilities, right? So that kind of a behavior is not something you had in Markov chains, right? And so maybe, so for example, see this transition. There are two self loops here, right? In the state warm, there is a transition on fast and there's also a transition on slow. Whereas in a Markov chain, you wouldn't have something like this, okay, like for each action. So that is one of the crucial differences. And of course, you have rewards also, the reward structure is there. So what is Markov about the MDP is just that, here again, what is random is the states, how the states evolve, but there's an additional action that comes in. So it's just that probability that, at any time step, st plus 1 equals some s, given, the other sources of information here is, of course, you have where you were at st, you have what action you took at time t, then you have what happened at time st minus 1, at minus 1, like that. Okay, and all the way till maybe s0. Okay, so this is the entire information about the evolution, okay, of how your states evolve, what actions you took, etc. So this probability actually just depends on these two quantities. Okay, so it just depends on what happened in the time step before. So this is just the probability of st plus 1 equal to s, given the state that you were in at the previous time and the action that you took at the previous time. So this is the Markov assumption in MDPs. Okay. So basically, the Markov assumption is always telling you something like, independent from it's conditionally independent of the history. Okay, just the most recent actions or most recent state of the system. Those are the things that help you decide where you will be in the next state. Okay, in the next time instant. Okay, so I hope this notion is clear about the Markov assumption. And we saw all this notion of time steps and all that. And there's also one interpretation I just wanted to give about, this randomness in the system. Okay, so that will help, as we go ahead also. So maybe let me just write it in the next part. Yeah, so you see that there is some randomness, right, associated with each action, right, where you, after an action, like where you will end up is not clear. So if you think of, the process, what happens is you start at some state S, okay, and then maybe there are different possibilities. So you take one action. Now you don't know for sure exactly where you're going to be. So you can think of it like a temporary state where it's not clear what is going to happen. And this many times, because there's a randomness, so this you can think of as, the environment. So around the agent, there's an environment, and the environment is going to decide which one of the states manifest. Okay, so there are different possibilities, and the environment comes into play. It does something, and that makes you go to S dash. So you might have thought that if you take an action, you will maybe lead to this state, but the environment came and did something, and so you landed up in S dash. Okay, so that is one interpretation. Now at S dash, so suppose now you come to S dash, then again you take another action, maybe A dash, and then again the environment comes in here, and after that you land up in some state S double dash. Okay, so this is the kind of underlying process that happens. So this should remind you a lot of the concepts you learned in multi-agent. So it's as if there are two agents here. One is you yourself, and the other is an environment. Okay, so the environment, it's not an adversarial environment, but it's taking one of these several actions. So it's like a random agent who comes in, and so you have to make some actions in the face of this environment. Okay, but of course you have rewards for each of these actions and all that happens. Okay, so any questions on this?
Ma'am,
Okay.
so the job of the environment is only to add the randomness or
Yes.
anything else?
Yes, nothing else. So unlike the case of, like Minimax, or I think even the other case like Expectimax also, I mean, in Expectimax maybe not, but in Minmax, the other agent had this job of trying to maximize its rewards. But here there is nothing like that. The environment is just going to come in and put some randomness. Okay. So it's like, even this robotic controls, right? I mean, there's a lot of components in the system. So you have designed it in some way, and there are different people who have come together and built the system. So now when you try to do some controls, if you try to do some action, you want it to move in some way, most often it will happen, it will move in the way desired, but there is a chance that it might not also, because there are a lot of these components. So if something goes wrong, it might not behave as expected, right? So it kind of models that kind of phenomenon. Okay. Yeah, and these intermediate states, right, where the environment comes into play, these are called, there's a name for it, these are called Q states. Okay, so it's like a temporary state. It's a function of, the state where the Q state is a function of what state you started from and what action you took. Okay, and so there'll be like a value associated with the Q state, and there'll be a value associated with other states. Okay, so there's some distinction here. For the purpose of MDPs, it's not very critical to have this term, but later when we do reinforcement learning, this Q state idea would be important. Okay, so yeah. Okay, so yeah, so these are some things which I kind of missed pointing out in the previous time, so I just wanted to tell you. And we also looked at this notion of utilities. So now each of the actions has some kind of a reward. Okay, and what you want to do is this process which goes on for possibly infinite time, and you want some notion of what kind of reward sequence is good. Okay, so for each action you're getting a reward. So how do you know what is a good reward sequence or what is not a good reward sequence? So to do that, you need some way to aggregate all the rewards that you get. Okay, and we saw some examples of just summing up the rewards. Okay, and we saw that this can go towards infinity, and so we can't really compare reward sequences when that happens. And so this led us to another kind of reward structure, where what you did was the immediate rewards, you gave more importance to that. Okay, so if you get a high reward in the immediate time step, then that you prefer more than a reward at a later point. So something like this example. Okay, so an immediate reward is always more preferable, right? And so that's why we had this factor gamma which came in. And so you just didn't do a sum of all the rewards, but whereas what you did was you kind of scaled each of the rewards at the subsequent time instant with gamma square like that. Okay, And yeah, so this gamma, there's a name for it. So it's called a discount. Okay. So basically what you're doing is at the next instant, you are discounting by a factor gamma. Okay. So at time 1, you discounted by a factor gamma. At time 2, you discounted by a factor gamma square, like that. Okay. So maybe let me just say that the cycle starts at time 1, because that may be a little more easier to, gauge the expression. So R1 gamma times, okay, so maybe the other way was only better, fine. Gamma, so you can just write gamma power T times RT, right? Okay, so I think this was fine. Okay, so we saw these examples, and so finally, whatever the reward that you accumulate, that we also refer to as the utility. Okay, and so we saw that because of having this kind of discount structure, or I called it a dampening structure in the last time, but let's just say it's a discount. And because of this discount structure, what happens is, of course, as you go along, the overall reward or the overall utility, it will converge to some number. Okay, whereas if you just did not have these discounts, or if the discount was a value of 1, then you were never guaranteed that you will, the finite utility would not be guaranteed. Okay? So these are some things we saw. And so this is something we have done. We have set up the MDP now. So what is it that we want from the MDP, right? In the case of search problems, we said that we want a plan, so which was a sequence of states, right, that you go. I mean, there also it was a sequence of actions rather, but which took you from the start state to the goal state. Okay, so what is it that we want here? Of course, we defined the rewards, we defined the transition functions, and all these actions, all these quantities we defined. So what we want here is what is called a policy. Okay, so we also saw something about policies earlier. When we talked of the min-max agent and the expected max agent, it was like a strategy that we set for this state, what action should you take. So it's the same thing that we want here. Okay, so policy just tells you that for each state, what action should I take? If I'm at a state, S, what action should I take? Okay, it's basically the same thing, but there's some difference in the way that you will compute this due to this randomness that comes in. Okay, and because of the randomness and the rewards. So what I want to just show you is another example MDP. Maybe that will make some things a little more clear. So what I want to do is use this MDP called the Grid World MDP. So you will be working on this in the next one. There's some time for that anyway, but the next part of your assignment will be based on MDPs and reinforcement learning. So there's this famous example called Grid World. Okay, so this is something that most people use this as a test bed to try out their algorithms. So let me just show you that. Okay, so there is there's a grid world setup here. I'm just running it manually to show you what it is. Okay. So is this visible? Is this grid visible? You see some squares?
Yes, ma'am. Yes.
Yes.
Yeah.
Yes. Okay. So here what the setup is like this. So the blue part is where I am right now. So there are these multiple locations where you have to go around. And so you can go anywhere. You can go up, right. There are all these actions, just like how you saw in Pac-Man. And what happens is there are these two special squares on the top right. Okay, so the top rightmost one, it's a special square. It has a reward of 1. Okay, so if you come here, if you somehow manage to navigate your way and reach this square and you exit from here, from this top rightmost square, you will get a reward of 1. Okay, but whereas if you come to the square just below and you exit from here, the reward is going to be -1. Okay, so these are the terminal states. So after this, once you reach each of these states, there is no more actions possible. You just have to exit. Okay, so this is the setup. It's like it's like a search problem itself, that you want to get from one place to another, but there are some places which are prohibited. Okay, that is one thing, and also there is, if you say that you're going to go up, it's not always guaranteed you will go up. There's some probability of going right. Okay, so let's just do it. I'll just see how it goes. I'm just doing it in manual mode. So just observe what gets printed on the terminal also, because it will tell you my moves, whatever I'm doing. Okay, see, so I took an action north. So actually I pressed the up arrow, but what happened was it moved right. Okay, so this is what is coming as random, and so this is the environment is doing something. Okay, so that's the idea here, and the reward here was 0. There's no rewards for any of these other states. The only rewards you get are in these 2 states in the top right. Okay, so let me take one more. So now I've come here, so now I have to see what to do. Okay, so again I took a right, I took an east, so now it went as planned. I went north, but it's gone left. Okay, and okay, so now I took a west, and it went west. I went up, it also went up. I went right, right. Okay, now I came to the terminal, so it's an exit state. Okay, so this is one run of the game that I've shown you. So I quit from the terminal state. I went to the good state in some sense, which gave a reward of 1. That action had a reward of 1. I got that, but see, my overall reward is this. It's not 1. Okay, so why did that happen?
You
Any
took more
thoughts?
time. Time over
I took
actions.
more time. Exactly. So that's the reason why I didn't get a full 1. So this is where the discount played a role. Okay, so here for this example, the discount was, I think it was 0.9. Okay, so yeah, it was 0.9 power how many ever steps I took. So that is this reward. And because none of the other actions had a reward, okay, so the only reward I got was in the last, only positive reward I got was in the end, but that was scaled by gamma power something. Okay, so this is one example. I mean, it's realistic in the sense that it also tells you how agents would navigate in the presence of some randomness. How should you navigate? Okay, yeah. So this is one thing, and there are different variants of it. Maybe I'll just show you one more variant. That is the example of this this bridge crossing. Okay, this is a bridge grid. So let me just show you that also before we go further. Okay. Yeah. So this is another setup. It's a different kind of a layout. So here it's the same thing. I have to somehow navigate my way through these grids so that I get good rewards. But here you see there are a lot of bad states. So these ones on top, okay, these 5 states on top and these 5 states on the bottom, they are like very bad states. Okay, so if you end up taking a transition to each of these states, there's a the reward is like -100. Okay, of course I've told you that the rewards are associated with the actions. Here they've written the rewards for the states. It's just what they mean is if you take an action which comes to these states, you are going to get a -100, and that's like the terminal. So these are terminals, and after that there is no way out. Okay, so there is one on your left. So the blue is where I am right now, and on my left there is, if I go immediately left, I'm going to get a reward of 1. But if I manage to go all the way right without wobbling to either side, then I will get a reward of 10 units. Okay, so so there's some dilemma here, right? So I mean, if there was no randomness, if you had full control however you dictate it's going to behave that way, then it's obvious, right? You just go straight to the 10. You just keep on going right and you will get 10. But now there is a possibility that you will end up jumping into these other other states which are like bad states. Okay, so that's the dilemma. Also now, by the time you reach 10, maybe there is also a discount that comes in, or should you just play safe and get a terminal reward of, a reward of 1, right? So these are the kind of questions that are asked in this kind of a setup. Okay, so you can think of these as the -100 states as like danger states. Okay, so maybe there is an agent is going in this way, but these are like accident prone zones, or maybe it's like there's some fire or something like that. Okay? So yeah, I hope the motivation for doing this kind of sequential decision making is clear to you all. So I just wanted to illustrate these examples to you. Okay, so now the thing is, we want to find a policy. Okay, so let's just come back to what we were doing. So in each state, what is the best action that I should take? So that is what we call as a policy, and that's represented as pi. Okay, that's the notation we use to represent a policy. So it's like, again, a lookup, but reflex agents also do something like that, right? They just look up and do as per the policy. But here you're computing a policy a little more intelligently. Okay, so that's what the goal of the MDP is. What is the best policy to you should follow? Okay. So let me just tell you a little more on how you can evaluate a policy. So just some more insight. So what you have as policy is like a function from a state to the set of actions. Okay, so for each state you have this function. So this is an action that you should take at action that the policy gives you, that the policy pi prescribes at state S. Okay, so now we also have what is called the value of a policy. So let me just write it this way. So value of a policy. So this is actually a vector. It's as big as the number of states that you have. So let me just write what it means for a particular state. So this is a value of policy pi under state S. Value of policy pi for state S. What it means is that at every step of this process, at every time step, you are going to follow what pi tells you. So you will be in a state S. Now, what action you're going to take is pi S. Okay, you'll take this action and the environment is going to do something. You will reach S dash. Now, you take the action suggested by pi S dash, and the environment puts you in some state S double prime. So all these are environment controlled. Okay, so this is environment control, and this is what you take as per the policy pi. So this goes on and on. Okay, so always you're going to follow what the policy pi tells you to do, and then what is the value you get. So this is like what is the utility you get. So it's actually the utility you get at state S, if you follow this policy pi. Okay. So let's just try to, write this down. So you just need to follow the, MDP, the evolution process. So where it starts at S, now you take pi S. So you land up in a Q state, and then maybe you reach S prime like that. Okay. And this goes on. So what is going to happen is the value here. So the value at the state S. Okay. So here, what action you're going to take is pi. Now, so I'll just define one more quantity. So this is called QS pi S. So remember, this is a Q state. So the value that associated with this kind of a temporary state, that I will call it as QS of pi s. Okay, so in general, so maybe I'll just maybe I should write it here itself. Okay, so in this kind of a state, you are going to have a kind of a utility associated with these states. So this is the utility associated with the Q state. Okay, and there is also value of S. So the value associated with this state. So that's the thing, and of course it depends on what policy you're going to follow. Even this Q is going to depend on what policy you're going to follow. Okay, so let me come back here. So there's a QS pi S. Okay, so you have taken an action pi S from starting from state S, and so the value here. Okay, so let me just write it here. So value of this state is v pi of S. So can you tell me what that is going to be? If I told you what the Q values are, right? So what is this value going to be?
Max of all queues.
So max of all Qs, is it? So why is it max?
Because we want to maximize our
expected value of all queues,
Expected value of
all possible actions, all QS pi s.
QS pi S, but here you see like you're going to, the setup is like you're going to always follow this policy pi. Okay, so we're trying to evaluate what this policy means for you. So now what you're going to do is whatever, somebody told you to take this action pi S, you're going to do that. Okay, so you're not going to compute the max right now. We'll come to that later. But right now, you're just going to do what the policy asked you to do. Okay, so if you know the value here, okay, at the Q state, so this v pi of S is just exactly this, right? Right, because you'll start in S, you'll take an action pi S, and this is now deterministic, okay, because you've come to this Q state. And this up till here, there is no randomness. Okay, now is where the randomness will play. Okay, so somebody said about expectations. Yes, that is correct. So I just wanted to, decompose it. I just wanted to, give some more details before coming there. So now if you want to find this value, Q of S pi S. So now the value of this in this state. Okay. So the value of this is an expectation, right? Now there is some randomness. You took this action pi S, but now the environment can come in and maybe choose any of these states. Okay, so what is it going to be? Can you tell me? Try, right?
Be the sum of probability into the value of S dash.
Value of S dash, exactly, right? So let's just write that properly. I'll just write it here, okay? So QS pi S dash. So it's exactly what who said. Sorry, I didn't see the names.
It's Umang.
Okay, cool. So like Umang said, so it's an expectation you take. So an expectation is just a sum over all possible states that you could be in. Now, what is the probability of being in this state? So that is, you started with S, you took an action pi S. So let me just call, this is a transition function, right? So transition function was this. So S pi S, and you reached the state S dash. Okay, so this is one possibility. And now you need to have the reward or the utility of the state S dash. Okay, so what is going to happen here is that, so now there are a couple of things, right? So an immediate action that you take is going to give you the first reward, right? So you had this quantity, reward S, pi S, S dash. Okay, I'm out of space again. Let me write it the next line. So this is product of this transition probability times something, whatever the value you're going to get on being at S dash. So that value has some components. So the first time you come to S dash, you're going to get a reward. So not A, so this is pi S times S dash. Okay, so reward, this is like a one step. The immediate reward is this. Now, once you're in S dash, again, it's going to go on, right? You're going to follow pi S dash here, and you will reach another Q state. And then some other set of actions, some other set of states will follow. Like that, it's going to go on. Okay, so what is going to happen is after this, you're going to get a reward of V pi S dash. Okay, if you follow the policy pi. So remember, that's how we defined V pi. So the value of policy for state S, right? So it's like if you start at that, going further, how much value you will get. Okay, so this is there. Now there's something I'm missing here. Can somebody tell me what it is?
Gamma.
Gamma, right? So in the next state, so in the next time instant, I'm going to get V pi. It's as if I'm from there on, I'm going to get V pi, but that has to be scaled by gamma. So that's a discount of gamma that you need. So this is the immediate reward. Okay, immediate reward. And this is the reward that you get after one time step. The one time step. So again, now this V pi S dash is again going to have the same structure, right? It's going to be like, it will be one of the Q S dash pi S dash. It's going to be exactly Q S pi S dash. And that is going to be an average over, the possibilities in the next time step. Okay, so so then what is going to happen is at time step 2, whatever you get is going to get again multiplied by a factor of gamma. So together there'll be a gamma square factor coming in for those rewards. Okay, so is this clear how you compute the value? The expressions, how you compute we will see, but are these expressions clear or is it confusing, or are there any questions on this? Okay, many of you are quiet.
Ma'am, like if the reward
Please,
is negative,
Mhm.
so gamma square will make it positive, right?
No. So gamma square, okay, so gamma is always a positive quantity. It's a discount. So this, if the reward is negative, this quantity, this R of S pi S dash, that will be negative. Okay, and so maybe, so when you have, okay, so this quantity again, so this will be Q S dash of pi S dash, which is again an expectation. So there'll be some other possible S double primes. There'll be a probability. So I'll just write it to indicate. So there's a probability times the reward you get at that point. So this would be the reward that you get when you start with S dash. You follow the policy S dash, follow the policy pi and you reach S double prime plus a gamma of V S double prime, right? Right, so this is what the V pi will do. So this is actually V pi of S dash. Okay, but so when you bring both in, what is going to happen if you expand this further? There'll be an R S pi S. I'm just writing the one in the square brackets. Okay, so R S pi S S dash plus gamma times again the summation where S double prime, there is this probability times a reward, right? And there's also going to be, so I'll just write it explicitly. So there is a gamma, there's a summation S double prime, there's a probability, and there's one more gamma. So this is gamma square times this probability into V pi of S double prime. right? So this is going to be the overall, this term in brackets is going to come this way, right? And this gamma square, this is greater than 0. But, the rewards, this will again have another reward component. That can be negative. So overall, there will be a negative term also that comes in here, right? I don't know if this was clear or
Yes, ma'am.
it's clear.
Could you repeat once, please?
Yeah, you want me to repeat the overall thing or this?
No, just the last one.
This last one. Okay, so you see, it's like a recursive definition, right? So this v pi of s is exactly this. It's q s pi s, but that is exactly this summation. This expectation rather. And so now when you try to find v pi of s dash, what happens? You take the action pi s dash, you will reach this intermediate q state. And after this, there'll be some s double prime, which shows up. That's going to be the actual state that you reach. So what will happen is this v pi s dash will again have all possible, states that you can reach, s double prime, times this, so this is summation over s double primes. The probability that you reach s double prime, given that you are in state s dash and you followed the action pi s dash, times the first reward that you get. So the reward associated with this move, right? So the reward associated with being at s dash, taking an action pi s dash and hitting s double prime. So that is the first term, this one. Okay. And from s double prime, again, there are different possibilities. The same process goes on. So there you will get an overall reward of v pi of s double prime discounted by gamma. So that is the next step. Okay. So it's as if you're starting the whole process from s prime. You're ignoring whatever happened before, and now going further, what is your reward? So you'll get this kind of a structure. Now, if you plug it back into the previous time step, so v pi s dash was whatever this expression was that I wrote here. Now, if you plug it back here, what you're going to get is the part in this part, okay, the square brackets. What you're going to get if the first term remains, then you're going to have a gamma times whatever you've written here, this one, v pi of s dash. So that would have this probability. So I'm just writing the same terms once again. So gamma, there's one gamma which comes here outside v pi. And so there's a gamma times this first term, summation, this probability times the first reward, the first time step reward. Then the next one, there's one more term here. So probability times gamma v pi s double prime. So this one. So that there is also gamma outside. So there's a gamma square times that. Okay, so gamma square times the summation over all possible s double primes and this quantity. So Satvik had this question of whether, because you have a gamma square, so does the reward end up becoming positive? So the reward will not end up becoming positive because only gammas are positive and gamma squares are positive, but the rewards you don't square it, right? The rewards come up as it is. So this will again, expand further. You'll have one more reward plus another gamma. So you'll have a gamma cube times what happens in the third time step. Okay, I don't know if I confused you all. Is this clear, Advait? It's clear? Okay. I wanted to also do one example for this computation. Maybe that would make it clear, but I'm kind of running out of time. So what I suggest is, we had this example, right, of this transition, this robotic car example, right? So try to, write down these recursions as a homework. Just try to write these, just follow this kind of steps and write it down for that MDP that we wrote there. It's a toy MDP, so it won't be too hard. But one thing I want you all to do is don't by heart these equations because it's very difficult if you by heart it. Try to think of this process that goes on and keep this process in mind, and then it'll be easier to write these equations. Okay, so just try it out. I will anyway discuss this again in the next class. Okay. So yeah, So we'll stop here. If there are any questions, I'll hand back. Otherwise, see you all tomorrow.